All right, what does it mean in mathematics for an equation to be implicit? What does it mean for an equation to be implicit? And so let me give you an example of an explicit equation. Y equals natural log x plus 2. That is explicit. And the reason why it's explicit is because y is given as a variable that's solved for. This is a function of x. Oops. Let's try that again. All right. This is a bad time for my tablet to die on me. There we go. Function of x. So in other words, Cody, y is solved for. There's nothing more to do. Does anybody want to take a crack at what the derivative of this is? dy dx? One over x plus 2. Yeah. And then when you use the chain rule, the derivative of x plus 2 is 1. So there you go. You're exactly right. 1 over x plus 2. No problems there. Okay? So, Zach, here's an explicit, here's an implicit equation. This is implicit. Why is this implicit? Well, what's the difference between this kind of an equation and the one that I gave you before? Y is not solved for. That's exactly right. Now what I can do, Zach, is I can turn this into an explicit equation for x. I could solve for x if I wanted to, but I'm not even going to worry about that, okay? It turns out that we can take derivatives of equations like these, and the derivatives mean the exact same thing that they meant before. So what I do is I take d dx of xy plus y squared equals 3. And the only thing I do different, Cody, is I assume that y is a function of x. I said the only thing I do different. It's not even different. That's exactly what I've been doing all along. And that's what I've been teaching you all along. So this is the way that it works. What I do is I take the derivative of each part. So do you see that for this first part I have to use the product rule for xy? So first times the derivative of the second. So this becomes x dy dx. That's the derivative of y whenever you do an implicit derivative. Plus 1y. The derivative of x is 1, so 1y. Plus, what's the derivative of y squared? What rule of differentiation do I have to use to take the derivative of y squared? Power rule. So this becomes 2y, and then by the chain rule, dy dx equals, and then what's the derivative of a constant? 0. Now where is this coming from right here? This is just coming from the chain rule. That's all that's doing. Whenever you take the derivative with respect to x of a variable y that is a function of x, you get dy dx every time. So this is not new, different derivatives. These are not new derivatives. Same rules apply. Now what I have to do here, Brian, is I have to solve for dy dx. I have to solve for it. So to solve for dy dx, I get everything that's not a dy dx on the other side of the equation. So what is the one term here that's not a dy dx term? Y. So I'm going to subtract y to the other side. All right, so what that's going to give me is that's going to give me x plus 2y in parentheses dy dx equals negative y. And then I divide both sides by x plus 2y, and I get dy dx equals negative y over x plus 2y. And that right there is the derivative, which by itself is implicit. But what you need to know, Yvonne, is that this is still the instantaneous rate of change for every point on the original curve. And what was the original curve again? xy plus y squared equals 3. Was that it? Okay. Now, here's an ordered pair which satisfies this equation, 2 comma 1. Cody, if I put 2 comma 1 into this equation, I get 3 equals 3. So this is an ordered pair which satisfies this equation. So I can actually tell you the slope of the tangent line at the point 2, 1 by plugging 2, 1 into this equation. So if I take dy dx and set x equal to 2, y equal to 1, I get negative 1 over 2 plus 2 times 1, which is negative 1/4. And that means the slope of the tangent line is negative 1/4. So even though the equation is implicit, it's different from what you're used to. It's exactly the same thing. Okay? And we're going to practice with this. We're going to do a lot of practice with this. So let's see if my program can handle this. I'm going to go ahead, go to my 2D grapher program, and I'm just going to plug in xy plus y squared equals 3. Yep, there's the graph right there of the implicit equation. Oh, by the way, notice that the equation is not a what? It's not a function because it doesn't pass the vertical line test. So what we're doing, Zach, is we're learning how to take derivatives of relations. Not just functions, but relations. Now, if I figure out, let's see here real quick. We've done tangent lines before. I've got the slope. M is negative 1/4. So how do I get the equation of a tangent line if I know the slope and if I know the point? How do I get the equation of the tangent line? You can. That's a good algebra 2 way of doing things. Point slope form. Y minus y1 equals m times x minus x1. So the slope is negative 1/4. So y minus 1 equals negative 1/4 x minus 2. So what I'm going to do, Cody, is I'm going to put this equation right here, y minus 1 equals negative 1/4 x minus 2, into my program, and I'm going to show you that it is a tangent line. Okay? So let's type that in. So y minus 1 equals negative 1/4 x minus 2. Voila. Let's just zoom in real quick. Do you see the red line right here? It is a tangent line. Exactly like what we've been doing with functions. Okay? So my first encouragement to you is that implicit differentiation is not a new differentiation. It's the same differentiation except the equation this time is not a function. It is implicit. It's a relation. Okay? All right, let's do some practice with this real quick. Let's go ahead and open up your textbooks to 4.3. And we're just going to dive right into the homework. Okay. And let's go ahead and go straight to these guys right here. So let's go ahead and do number 11. X squared plus y squared equals 100. Okay. It says find dy dx by implicit differentiation. So what we're going to do is we're going to assume that y is a function of x. Zach, whenever you see me write this on the board, y arrow y of x, that's what that means. That means y is a function of x. So what's the derivative of this? First part, we're going to take d dx of the whole equation, x squared plus y squared equals 100. All right. What's the derivative of this first part here? Good old power rule. 2x plus, now use the power rule again, so this would become 2y, but then by the chain rule, dy dx. So basically what's going to happen is whenever you take the derivative of an expression that has a y in it, it's going to end up with a dy dx at the end. It's pretty much the way that's going to work. Is equal to, okay, what's the derivative of a constant? Yes, ma'am?
Okay, is that just to make sure that, like, if y was something more complicated, we get the derivative?
That's exactly correct.
So that's just saying take the derivative of y?
Right. Now, dy dx, if you want to think of it this way, dy dx is a black box, which means this. If I knew what the actual equation was for y, if y was equal to natural log x, let's say, then dy dx would have to be 1 over x if it was the natural log of x. So we consider dy dx to be a black box, which means it's mathematically correct, but we can't go any further with it analytically. What's the derivative of 100? 0. All right, what do we do now? Yes?
So why don't we put the dy dx after the 2x as well?
Because we didn't take the derivative, because there is no y term here, we didn't take the derivative of y with respect to x. We just took the derivative of x with respect to x and got 2x. Actually, technically what we got, Tori, was 2x dx dx. And doesn't cancel, but it becomes 1. Now, you actually bring up an excellent equation, an excellent question. Cody, if I had x squared plus y squared plus z squared plus w squared equals 10, you don't have to write this down. And if I took the derivative of this, it would be 2x plus 2y dy dx plus 2z dz dx plus 2w dw dx equals 0. Because what you would be doing is you would be assuming that y, z, and w are functions of x. You wouldn't have to put dx dx at the beginning because if you take the derivative of x with respect to itself, it ratios out to 1. So there's no reason to do that. So you can take derivatives of multivariate equations now. Does that kind of make sense? A little bit? Okay. This part you don't need to write down, so you can just forget that. Okay, what do I do here now?
Subtract the 2x.
Okay. So I want to solve for dy dx. Yeah, so I subtract the 2x, so I get 2y dy dx equals negative 2x. Divide both sides by 2y, so dy dx equals negative x over y. Now, let's look at the original equation real quick. X squared plus y squared equals 100, and dy dx equals negative x over y. Is it possible to take the implicit equation and solve it for y? Is that possible? Yes. What do I have to do to solve this equation up above for y? Yep. And then square root. So I'm going to end up with y equals plus or minus the square root of 100 minus x squared. Now here's the thing. This is what I want to teach you. even though the derivative was implicit, because I can make the equation explicit, I can now substitute that into the derivative and make the derivative now explicit. So you're not always stuck with implicit just because you start with implicit. But sometimes you are, but not in this case. So what this becomes is this becomes negative x over plus minus square root of 100 minus x squared. Now remember, this is not a function. It's not a function. Why is that not a function? It's basically the same thing? What do you mean by basically the same? You talking about the signs? No. The one on the left, this one?
Up there.
Up here? This equation is the same as this equation.
Yeah.
That's correct. When you solve an equation, everything should be equal all the way through, so you're absolutely correct. This equation is equivalent to this one right here. So this derivative then is equivalent to this derivative. The only difference is that this one is implicit and this one is explicit. That is the only difference. Okay? Okay. All right, let's just work another one. Let's take this one. X squared y plus 3xy cubed minus x equals 3. What rule do I have to use first if I take the derivative? Product rule, yeah. Okay. First times the derivative of the second. So this becomes x squared, and then what's the derivative of y with respect to x? dy dx. Plus second times the derivative of the first. What would that be, Brian? Second, which is y, times the derivative of the first. So I'll just put 2xy. Y 2x or 2xy, they're the same. All right, now I have to use that product rule again, okay? So Cody, first, which is 3x, times the derivative of the second. What's the derivative of y cubed with respect to x?
3y squared.
You got it. So what this becomes is this becomes 9xy squared dy dx plus second times the derivative of the first, 3y cubed, minus, now the derivative of x, oh, this is easy, 1, equals 0. Okay, let me put the brakes on there. Any questions up to this point? Perhaps where did I get the 9 from? Does that make sense, where I get the 9 from? This one right here? That came from the product rule. When I take just the derivative of this, 3xy cubed, this is the first function, this is the last function. So first d last, so there's my 9xy squared dy dx, plus last d first, so 3y cubed. Does that make sense? That's where that came from. So I had to use the product rule how many times in this problem? Twice. I had to use it twice because I have two different products. Okay. Now we're going to solve for dy dx. So we put everything that's not a dy dx on the other side. So I get x squared plus 9xy squared dy dx equals 1 minus 2xy minus 3y cubed. And really what you're going to do now is you're going to divide both sides by x squared 9xy squared. And there is the derivative. That right there is the instantaneous rate of change for every point of the original equation. Now, algebraically speaking, with what we've learned so far in algebras 1 and 2 and pre-calculus, do we have a way to solve the first equation explicitly, meaning getting y as a function of x? Do we have a way to do that? Not at least in the algebras that we've taught you here, no. This is called a cubic equation for y, and so it turns out that there is a formula that you can use, but it's a very complicated formula. It's way more complicated, Jacob, than the quadratic formula is. So we just say, good enough. We don't try to solve it explicitly. Okay, so sometimes, Zach, you're going to differentiate an implicit equation and you're going to end up with an implicit derivative and you're going to leave it as an implicit derivative. Nothing you can really do. But sometimes you can do something about it. Okay? All right, I'm going to prove to you that this is exactly the same kind of differentiation. Okay? So, let's go back to something easier. Y equals 1 over x. What is the derivative of y equals 1 over x? So in other words, what is dy dx? What rule do we have to use here? Quotient rule. Low d high minus high d low all over low low. So low times d high minus high times d low all over low low. What do I end up with here, Brian? Negative 1 over x squared, and that's the derivative, right? That makes sense? Okay. Now, Cody, can I convince you that this equation is the same as this equation? Okay. This equation right here is implicit. So I'm going to use the same rule that I did before, except I have to use the product rule. So first times the derivative of the second, x dy dx, plus second times the derivative of the first, done implicitly. Solve for dy dx, right? So dy dx equals negative y over x, and I end up with an implicit derivative, right? Okay? But wait a minute. I can replace y, and what can I replace y with? 1 over x. So this becomes negative 1 over x, and that simplifies to negative 1 over x squared. So the implicit derivative and the regular derivative, they're all the same, folks. They're all the same. The only thing that's different is, can you substitute explicitly? A lot of times you can't. A lot of times you can't. So you just kind of leave it. Okay? All right. Take a shot at number 15. I'm going to give you a couple minutes on that. Take a shot at number 15. Okay, so 1 over y plus 1 over x equals 1. What did you get, Ralph? Dy dx equals?
Negative 1 over x minus 1 squared.
X minus?
No, like this.
Down here?
Yeah.
X minus 1. And then parentheses?
Yes.
Okay, parentheses squared. Okay. And that it right there? Okay. All right. Did anybody get an implicit form? Okay. Did everyone get this? Okay. So here's what we do. We take the derivative at the beginning. So what I want you to do right now, focus just on this. What rule do we have to use here? Quotient rule. So low d high minus high, what's d low? dy dx. All over low. That's the first part. Now this next part's not so bad. Now we concentrate on this. What's the derivative of that?
You just want it.
Yep.
Negative 1 over x.
Negative 1 over x squared equals 0. Okay. Let's simplify this a little bit. Y times 0 is 0. Can I convince you that this is negative 1 over y squared dy dx minus 1 over x squared equals 0? Can I convince you that that's true? Since this crosses away, we're left with this. All right, add this to the other side, so negative 1 over y squared dy dx equals 1 over x squared. Now I have to divide both sides by negative 1 over y squared or multiply by the reciprocal, either way. So dy dx can equal 1 over x squared over negative 1 over y squared, which simplifies anyways into negative y squared over x squared. Is that what you got? All right. Now, Ralph's answer, what's the difference between Ralph's answer and this one? Ralph's is explicit. So what Ralph probably did is he solved this equation over here for y. So let's take this real quick. Let's save this for just a second. Let's take the original equation, 1 over y plus 1 over x equals 1. What's our first step here in solving this for y? Multiply by xy everywhere. That's exactly correct. So xy distributes into the equation, and I get x plus y equals xy. Subtract y to the other side, so x equals xy minus y. Factor out a y, so x minus 1 times y, and divide. So I end up with y equals x over x minus 1. Now let's go back to our implicit derivative. We had negative y squared over x squared. So I substitute this in. What I got here I substitute in. So I get dy dx equals negative x over x minus 1 squared over x squared, which is equal to negative x squared over x minus 1 squared, and these divide away. So there you go. So there's the explicit form. And the other one, negative y squared over x squared, is the implicit form. And for this lesson right now, unless the directions tell you, I'm going to use a pun, explicitly, unless they tell you explicitly to put the derivative in the explicit form, what I'm looking for is for you to find the derivative however. Okay? But knowing how to take an implicit and put it into the explicit is a skill that you need to develop. We're not there yet. Okay? All right. Questions, comments, concerns? It's more amazing than you thought it could ever be. Okay, no takers on that. Let's see here. I would like you to, actually, let me open this up real quick so that you know where we're going here this week. This is going to go up on my board shortly too. Okay. In calculus this week, the homework tonight, this is the evens, 2 through 32 evens. And that's tonight. Tomorrow is the second part. That's 36 through 56 evens. So I have to hit this section harder than what I normally do. That's Tuesday, so that's the assignment on Tuesday, 36 through 56. Wednesday, we're going to have a quiz, and that quiz is going to cover 4.1 through 4.3. 4.1 through 4.3. Then Thursday, we hit the derivatives of inverse trig functions. That's a joy. So the lesson there, the homework there is 2 through 20 evens. That's Thursday's assignment. That's going to be going up on my board. I just haven't had time to put it up there yet. And then Friday is the second part of that lesson, and that's 22 through 36 evens. And then that finishes chapter 4, I think. Maybe there's one more section.
What was Thursday?
Thursday's homework is 2 through 20 evens. So that gives you a synopsis of the week. All right. God bless you.